Welcome to solverfy.
In this question, we want to calculate the wavelengths of the first 4 transitions in the Balmer series of the helium plus ion. We want to compare these to the wavelengths to the same transitions in a hydrogen ion. So we're given the Rydberg constant for helium ion in joules. Since we're given the Rydberg constant in joules, we have to use the following equation in order to calculate this. So, first of all, I calculated the transitions for hydrogen. So for hydrogen, the Rydberg constant is 2.18 times 10 to the negative 18 joules. And the Balmer series always ends with energy level 2. And then the final energy level is just going to be 3, 4, 5, and 6 because we want the 4 transitions. So basically, I plugged in the values. And then if you plug in the values and we do the math, we end up with the wavelength. So keep in mind that energy is interchangeable with Hc over wavelength. So we could also say that this delta E is Hc over wavelength. So that's how we're able to get just the wavelength. So you can see I showed the math here. And keep in mind that H is Planck's constant, c is the speed of light, and our units have to match. So as long as we have Planck's constant in joules per second and c in meters per second, we should be fine. We'll get the wavelength in meters because our Rydberg constant is already in joules. So we will get those units for the wavelength. So I did all the calculations and I was able to find the wavelengths for the transitions. So we would do the same thing for the helium ion. So keep in mind that Z is the atomic number. So it's important to know that helium's atomic number doesn't change just because it loses an electron to become an ion. It's still going to have 2 protons in the nucleus, so we're going to still have to plug in 2 for Z. So if we do the math, we're able to calculate the wavelength. We're just going to use the same formula we did for hydrogen. So let's compare the values that we get. You can see from 2 to 3, we have a wavelength of 4.10 times 10 to the negative 18. So let's take a look at what we got for hydrogen. That would be 6.57 times 10 to the negative 7. So it looks like this wavelength is longer than the wavelength that we obtained for the helium ion for this transition. And you see that that's actually true for all of the transitions. So in general, the transitions for the helium ion, they have longer wavelengths. So we could determine from the formula for energy that if we have a longer wavelength, so higher wavelength value, then energy will go down. So actually, in this case, it looks like due to the fact that we have longer wavelengths for the hydrogen transitions, the energy for the hydrogen transitions is actually lower. So we can say lower energy transitions for the hydrogen. Also, we can see that as we go through the different transitions, these transitions are differing by 10 to the first power, because we have 10 to the negative 8 as the exponent part of the transitions for helium, and we have 10 to the negative 7 for the transitions for the hydrogen.